Alright, so welcome to today's lecture series on Introduction to Computer Networks, and today's topic is going to be TCP IP model. So the objectives of this topic is to understand what the TCP IP networking model is, and also the OSI networking model, and we'll also try to establish the similarity and differences between these two models. So let's first have a quick recap of what a protocol is. A protocol is a set of guidelines which allows entities from different systems to communicate with each other over a network. There are conventions which includes the syntax, the semantics, and the timing of the messages which are exchanged between two or more entities with respect to a specific communication. So why do we use a protocol architecture? The reason that we apply an architecture when discussing protocols is because data communication is considerably complex. In the process of exchanging messages, we need to identify the path and also the receiver for our messages. We need to negotiate the common protocols and also the applications which are going to send and receive the data. Moreover, the way that our applications handle data and present it to users would need to be translated to supported file formats, which is not exactly the way network sees data, because we know that network and computers only understands binary bits. So we need a complete system which will allow us to support the transfer of the binary bits and then convert it into user understandable or presentable format. So what is the modular approach in networking? Basically, what we need to understand here is that we are going to try to break tasks into smaller subtasks in the process of network communication. The reason why we do that is because so that we can assign each of the subtasks into separate modules, and then we can design the individual modules accordingly so that they can handle the specific subtasks in a way that the overall communication is effective. And during the communication, the different modules on the same system, they communicate with each other, as well as similar modules on different systems communicate with each other through the network. So the overall advantage of modularity would be that we have an easier application development, so that anyone who wants to develop something for a network application or computer networks overall can focus on specific modules and design accordingly. Moreover, given that computer networks are subject to change at different times, we can say that we can swap out the different modules if something is updated for that module, and then we can continue the operation without all the programs being modified. So that gives us or brings us to the idea of the TCP IP networking model. So as you can see here, in the early 1980s, IBM came up with the first concept of this modular approach, and that's when the internet was coming alive with a more standardized format. In the 1990s, there were further vendors and standards being developed, and eventually in the 2000s, the TCP/IP model was standardized, which brings us to our current point of time, what we see in today's internet. So whatever that we will be studying or looking at here is going to be the current model of the TCP/IP networking that we have seen to be standardized so far. So the different protocols which are included in TCP/IP are defined in a set of documents. We call these requests for comments, or in short RFC documents. You can check out the list of RFCs in the RFC wiki page. And the idea is that TCP/IP uses standardized protocols. And in terms of standardization, there are many different organizations which help standardize different protocols. One of the most prominent of these organizations is the IEEE, or the Institute for Electrical and Electronic Engineers. And for example, the TCP/IP model is described in RFC 1122, the earliest version. You can check out the link to see how it's described. So this is the more technical description of what and how the TCP/IP model should look like. So let's come to the idea where we are integrating the modular approach into the TCP/IP networking model. So TCP/IP stands for Transmission Control Protocol. TCP/IP is Internet Protocol. So it's the TCP/IP model which was developed by DARPA, and what it does is that it defines a suite of protocols which can be used by different hosts and nodes on the internet so that they can communicate with each other. The idea is that each layer in the TCP/IP model supports specific protocols, and anyone who would like to be a part of the internet should be implementing one or more of these protocols. So the original TCP/IP model had 4 layers. Coming from the bottom, the link layer, the internet layer, the transport layer, and the application layer. However, it was recently updated over the last decade into the 5-layer approach, where the link layer was actually divided into 2. So now we have the physical layer, the data link layer, the network layer. This has been renamed from the internet layer, and the upper layers as transport and application. So we refer to as the bottom layers to be the link, the physical and the data link layers, and the upper layers to be the application transport layer. And the network layer is the one which sits in the middle and facilitate the upper and the lower layers. So let's try to go one by one and try to understand what these layers do and what they're responsible for in terms of the subtasks that we were talking about. So the physical layer, which is the lowest layer, defines the specific physical interface between terminals on the internet. In short, we can call them DTE. It defines the transmission medium. The specifications that we obtain with the protocols and the physical layer may include the characteristics of the medium. For example, if it is wired or wireless, the nature of signals, how this medium is going to send and receive the binary bits, what are the supported data rates for each of these mediums, so on and so forth, and how this overall modulation and interpretation of the bits would occur in the physical layer. So once we have established how 2 end systems would be connected physically, we then go ahead and try to define, once they're connected, how the data is going to be exchanged between the systems. And that is where we come to the data link layer, and this defines the exchange of data between systems on a shared network. This means that the physical layer just establishes the means in which the bits would be exchanged, whereas the data link layer defines how they will be sent and received to specific hosts and destination which are directly connected. It also allows you to prioritize transmission, and the software in this layer depends on the network type and also the physical medium which lies underneath. The reason why we have the data link layer separate from the physical layer is because this particular segregation allows whatever software that you have in this layer is independent of the physical layer. So that is why we can see that we can be connected to an internet through wired connection or a wireless connection and have the same internet connectivity. And that is what allows us to be independent of the physical layer. The third layer is our network layer. And the network layer handles the tasks between the upper layer and the lower layer, which is the data link layer, and the upper layer, which is the transport layer. And what it does is that it allows you to establish the interconnection of two or more networks. So now we are going a bit further. So rather than being connected directly, we are now connecting through multiple networks. The network layer is what that is responsible for IP addressing, something that we use to address hosts on a network, and also how each packet would be routed across the network. Next, we have the transport layer. It's also called the host-to-host layer, and this particular module or layer is responsible for ensuring a reliable exchange of data between applications. So now, instead of addressing the hosts, we are now addressing specific applications which are residing in the hosts. The two most common protocols that we have for the transport layer are TCP and UDP, and these are the protocols which allows us to create the application to application data channel between two hosts. Finally, the topmost layer, the application layer, it is the layer which allows you to create and support applications which can interpret the data and present it to the user accordingly. For example, if you have a file transfer application, or you have a voice chat application, or simply a video streaming application. So each of these applications would need different interpretation of data, and this is the layer that is responsible for supporting that. So if we try to kind of look at what happened here, so if we have a host connected to the internet, and the direct connection that we have is what that is defined by the physical layer, and then each of these applications, they may be connected to multiple other networks, and one of the networks might have a connection to another host. So the data link layer supports the physical connection and the establishment of the communication channel. Whereas if you're trying to send a packet from host 1 to host 3, the packet needs to go through multiple networks and reach host 3. So this connection and also the routing is facilitated through the network layer. However, we also know that each host may have multiple applications running on it. For example, a file transfer application, a video streaming application, a voice and video chat application, etc. So we are generally sending and receiving data from one application to another. So the way that we set up this connection from the application to another application in host 1 to host 3 is facilitated through the transport layer. And finally, the way that we present the data on the user end on both sides is facilitated by the application layer. So the common set of protocols that we have for the TCP/IP network model for the application layer, it could be HTTP for web browsing, POP3, which is post office protocol, which allows us to send and receive emails. SMTP is simple mail transfer protocol, which is also another protocol for sending and receiving emails. The transport layer protocols for TCP/IP, the most common ones are TCP and UDP. UDP is faster, but it does not guarantee that each packet will be delivered to the recipient. So an example of an application which would use UDP would be video streaming, where the latency is more important and you can actually ignore if a couple of frames are dropped in the middle, but the overall user experience is more important. However, TCP guarantees packet delivery but is slightly slower than UDP. So if you are running an application which requires a complete file transfer, that is where TCP would be more useful. The internet layer or the network layer uses the internet protocol. This is the backbone of the internet, which allows all the upper layers and the lower layers to communicate with each other. And finally, the link layer protocol. Protocols would be, the Ethernet protocol, the point-to-point protocol, etc. In the physical layer, we are looking at more at the physical media, which is wired and wireless, radio, all of these features. So in terms of the protocols, these are the ones which are interesting and would be important to consider. So let's try to look at how the HTTP application layer protocol works. Just a quick idea. The basic logic is to get a web page, and the web page is nothing but a file that is stored in another computer. So if this is the host that is using a web browser, we say that Bob is a user on a web browser and would like to request for a web page. So Bob sends a request to the web server, which is another node on the network and has a copy of that particular file, which is the web page. So when the web server receives the request from Bob, it sends back a copy of that file to Bob, and Bob can then view the file on his web browser. So if you're looking at the HTTP protocol a bit more in details, we have to understand the concept of HTTP headers. So HTTP headers are basically specifications for a specific HTTP request, and it directs the action that will be taken by the receiver of this packet. So when Bob from the web browser would like to get a copy of the home.html file, he sends the HTTP GET request, and he places the name of the file, get home.html, and sends this HTTP message to the web server. When the web server receives the GET message, it understands that now it needs to respond with a copy of that file. So it sends back an HTTP reply. So for the reply, it sends OK, which means that I do have a copy of the file that you are requesting. And then it starts transmitting the rest of the file. However, do note from the previous chapter that the network needs to break down data into multiple packets. So the file that the web server has might be required to be broken down into multiple packets. So if you see here, the first part of the packet is appended to the HTTP reply OK, and then it follows through by sending the remaining parts of the packets. So the web browser waits so that it gets the whole file and then can go ahead and start displaying the result. So when we said that transport layer allows or guarantees reliable delivery, So let's try to understand how the HTTP protocol would be using the services of the transport layer. So we have just seen that the web page is broken down into multiple parts. So the first part is where it sends an HTTP response OK, and then a part of the web page, and then some more, and then the remaining. So if you see here, it sends along with it something that we call a sequence number. So during transmission, when the web server is sending all of these packets to the web browser, one of these packets may be lost. So what happens is that the transport layer supports this feature where it can send back another packet to say that I did not receive packet number 2. So this is an error recovery service provided to the HTTP protocol in the application layer from the transport layer. So when the web server receives this request to resend packet number 2, so it will then send 2, and Bob will then be able to receive the whole web page. So the different layers that we have in TCP/IP, they interact with each other, and also they interact with the same layer in another node. So let's say we have a host trying to send and receive a packet to another host through a router. So we say that there is a physical connection from the host to the router. The host has the link layer to support the features of the physical layer. That means that whatever that is being sent and received by the physical layer needs to be going through the data link layer. And if you go higher, anything that is sent and received should be supported and should be through the network layer. The transport layer sends and receives information from the network layer, and the application layer sends and receives information from the transport layer. So now in the case of routers, routers do not have applications running on them. They are specialized devices which only allows you to route and forward packets, right? So that is why they do not have the transport and application layer support in its software suite. So the physical layer in the router, which connects to the host, communicates with the link layer. Then the network layer is what that allows two interfaces on the router to exchange the information back and forth, and allows it to forward the packets accordingly. And on the other end, the router has this physical connection established with another host, and this host again goes through this whole stack of layers to send and receive the information from the physical layer to the application layer and back. Now, the reason why we say that the layers are also interacting with each other horizontally is because an application on one host is able to interact with another application on the other host. Although it takes the path through all the layers, but the application layer itself feels that it is talking to the other application on the host. A good example for this would be, let's say if you are running a chatting application on one of these hosts, and whatever that you type here is appearing here, and then whatever that you type here appears on the other host. So the applications are given the feeling that they are actually talking to each other, although it needs to travel through all of these layers to be able to go to the other host. So same layer interaction on different computers occurs when there's a commonly agreed protocol to communicate with the other computer, and each of these hosts are using the same protocol and a way to interpret the headers for each of the messages which are being exchanged. On the other hand, adjacent layer interaction on the same host is providing a service to its adjacent layer. For example, the transport layer would provide a service to the network layer and the application layer. The network layer provides a service to the transport layer and also to the data link layer. So let's look at a quick example of how the postal service works, right? So this will help us in understanding how packets are actually routed. So in the postal service, if you are trying to send a letter to another person, you send it out to the postal service. The postal service has post offices across United States, and then your letter goes through this complex network of postal offices and finally reaches the destination. So the way that this packet travels might actually be different than the way that another packet may travel. And it may go to some other destinations as well. So this is the same concept that we have in the TCP IP network. Hosts on the network are given addresses, just the way that you have addresses in the real world. So whenever you are trying to send a packet from Larry to Bob, the packet would need to be addressed to Bob's address. To be very specific, you specify the sender address as Larry's address, and you specify the destination address as Bob's address, and then this packet would go through this network and reach Bob. So let's say if Larry has an address of 1.1.1.1 and would like to send a packet to Bob, whose address is 2.2.2.2, the packet would have the source and destination specified accordingly, and it will also say that this is a TCP packet and it is for the application HTTP. So if you see here, Larry is only connected to R1. So whenever Larry wants to send something, it will always be sent to R1. When R1 receives a packet, it has an option to send to R3 or R2. However, when Larry is sending a packet to the destination 2.2.2.2, R1 will see that the packet is being addressed to something in the family of 2 dot something. So it forwards it to R2. Next, when R2 receives the packet, it sees that the packet destination starts with 2, and this is a machine which is connected to its local network, and the destination is directly connected to R2. So R2 then forwards the packet to the correct destination, which is Bob, and the packet reaches its final destination. So if we go further down the layer, in the data link layer, we have the Ethernet protocol, which is the most common protocol for LANs. And what it does is that it has an operation that we call encapsulation. And what this means is that whatever packet that Larry is trying to send from the network layer would be encapsulated with an Ethernet header and Ethernet trailer. So now, after this IP packet is encapsulated with a header and trailer, the Ethernet protocol is now ready to transmit the data to R1. Next, R1 receives the packet, verifies the Ethernet header and trailer, and then looks at the IP packet and extracts it. So this specific operation where it extracts the IP packet is called decapsulate or de-encapsulation. So every time an IP packet is required to be sent from one node to another, it needs to be encapsulated by the Ethernet protocol. It reaches the other point, and then it needs to be de-encapsulated. And this encapsulation concept doesn't apply only to the Ethernet layer. It applies to every layer that is there in the TCP IP model. So when we were talking about the application layer generates some data. That data is fitted in the transport layer with a TCP header, or alternatively, if it is using the UDP protocol, it's going to add a UDP header. So after it adds the TCP header, it passes down to the network layer. The network layer adds the IP header. And The whole thing now is referred to as an IP packet. After that, the network layer passes it on to the data link layer, which is the Ethernet protocol. So this whole part in the middle is the IP packet. The Ethernet adds both a header and a trailer. And then the physical layer allows you to transmit the bits in zeros and ones. The same thing happens when the receiver receives a packet. The process just goes the other way around. The receiver receives bits, then discards the Ethernet header and trailer to obtain the IP packet. Next, it discards the IP header to get the transport layer data, and then discards the TCP header to get the application layer data. So going up, we are de-encapsulating. Going down, we are encapsulating.